Well, good morning. This is going to be an all-morning session, and there'll be two segments to it. The first will be radiometric dating, relative, not absolute ages. It'll be the longer of the two presentations because there's more to talk about and explain. Then we'll have a short break, and then we'll go on to talk about radiocarbon dating in need of recalibration. And I think you'll find that interesting. But we've got the time to look at this topic in a slower pace and trying to explain as much as possible to you. And I hope that you'll be able to follow through. If you have any questions, then certainly fire them at me. But when it comes to this question of radiometric dating, a lot of people, their eyes glaze over, but it's really not that difficult once you understand the basic technicalities involved. So the first question is, how are the ages of rocks determined? By colour or appearance. A, B, rocks come already labelled, high on millions of years old. C, by observing rocks form. D, by the minerals in the rocks. E, by the fossils in the rocks, or by the chemistry of the rocks. And we're talking about measuring the ages, okay? And the answer should be obvious, shouldn't be by the chemistry of the rocks, which is our subject this morning. And it's by assuming and utilising the radioactive decay processes. So each element of the atoms is made up of atoms with the same unique number of electrons and protons. The number of protons gives the element its chemical name. So for example, element 6 is carbon, and it has 6 protons in the nucleus. And to balance, of course, it has 6 electrons orbiting in its shells. Now, normally it would have the same number of neutrons in the nucleus. So a regular carbon atom is called carbon-12 because it has the 6 neutrons and 6 protons in its nucleus. Now, this should all be revision for you, but it doesn't hurt to go over it so that you understand the symbols that are used and their designation. And as I said, it also has 6 electrons to balance its charge. Now, the number of neutrons can vary. And so you have carbon-12, which is regular carbon, which is 6 neutrons in the nucleus, but you can have carbon-13 with 7 neutrons in the nucleus, and you can have carbon-14. It has 6 protons and 6 neutrons to make up its nucleus. But the problem is carbon-14 is unstable. You recognise that. Radiocarbon is carbon-14, carbon-14 dating, radiocarbon, and it decays. And the issue is that because of having 8 neutrons in the nucleus with 6 protons, it's getting a little bit crowded, and it's a little bit unstable holding all those particles together in the nucleus of the carbon atom. And so what happens is one of the neutrons in the nucleus decides to split, and it ejects an electron, and so it ends up now with 7 protons in the nucleus and 7 neutrons. So, and it has ejected electrons, so what does it become? It becomes nitrogen-14 because it's now got 7 protons, it's changed to a different element. And so that's the basis of radiocarbon dating, which we'll come to later in the morning. So we talk about the different atoms with different neutron numbers. We call them isotopes. And so we've got isotope 12, carbon-12 is the regular stable isotope of carbon. We've got carbon-13, which is also stable, and we've got radiocarbon or carbon-14. The 14 refers to the atomic weight, as we said before, which is the neutrons plus protons, and we call these isotopes of carbon. And so sometimes you'll hear people refer to it as radioisotope dating, which of course is short for radioactive isotopes. Isotopes that are, and radiocarbon is an example, where the radiocarbon is unstable because of the holding everything together in the nucleus, and so it decays to nitrogen-14. So
some of these atoms are unstable. I've talked about carbon-14, but one of the main ones is uranium-238, and you can see the chemical symbol there, U for uranium, of course, and 238. It's the radioactive isotope of uranium. And you get the isotopes, these unstable atoms, decay by ejecting these subatomic particles, and they decay in two different ways. There's beta decay, which I've already described to you. I have to, of course, always remind myself to say it's beta decay, not beta decay, because otherwise you mightn't understand, the southern pronunciation. You got to remember that it was the Americans that revolted. The rest of us stayed loyal to the Queen, and so we speak the Queen's English. Anyhow, jokes aside, there's beta decay and there's alpha decay. And beta decay is where a neutron splits into electron and proton essentially, and alpha decay is where the atom spits out 2 neutrons and 2 protons. And so that happens with uranium. And so there's bigger jumps in the changes and bigger particles that are emitted. But we'll come back to that again in time. So this process of change like that, and this is an important thing because during the RATE project we were talking about the possibility of accelerated nuclear decay during the creation week, and when people hear the word decay, they sort of but is it really a decay process? The quality of the daughter atom is no less good than the quality of the parent atom, and so it's really a process of nuclear transformation or nuclear change rather than decay. But it's been known as decay, and the problem, of course, is that part is okay. It's the radiation that comes off because you get residual energy that's spat out as gamma rays, and that's quite nasty, and so that's why people balk at this whole question of radioactive decay during the creation week. But that's a different story. So we have the radioactive atoms or radioisotopes result in stable atoms or isotopes of different elements because the transformation changes the number of protons in the nucleus, so one element transforms into a different element. And so we can talk about parent atoms and daughter atoms that are stable, and minerals, rocks, and even fossils contain some of these radioactive parent atoms that decay to daughter atoms. And I add fossils there because it is possible to date some fossils, and it's being done now using radioisotopes, because if you've got the equipment to detect the trace amounts of these parent atoms and daughter atoms, then it is possible to directly determine a radioactive age for a fossil. But then there's all sorts of other assumptions that come into that we don't have time to look at. But here are the different methods that are available to use. And you're familiar with carbon-14 or radiocarbon decays to nitrogen-14, and we'll come back to that as a separate topic in the next session. But there's two isotopes of uranium that are radioactive, 238 and 235. The dominant one is uranium-238. It decays to lead-206. Eventually through a chain reaction, as many of you are aware. And there's a series of steps involved, 8 steps. Uranium-235, of course, is the minor isotope, but it's the one that everyone wants to produce a nuclear bomb. And that's another story as well. There's potassium-40 decays to argon-40. Notice that you can tell the beta decayers. The beta decayers don't change the element, but they don't change the atomic weight of the daughter. Whereas the alpha decayers significantly change the atomic weight in the process. The atomic weight of the parent, the daughter is different, significantly different. So potassium decays to argon, which is a beta decay process, and rubidium-87 to strontium-87, a beta decay process. Samarium changes to neodymium It's an alpha decay process. Many of you may not have heard of the elements samarium, neodymium. They are one of the rare earth elements. And neodymium particularly is significant. Most of you are familiar with those wind farms. What you don't realise is that one of the elements that is important for those wind farms is the element neodymium. Why? Because neodymium combined with a regular magnet produces a supermagnet, and you need to have a supermagnet to get some traction in a wind farm situation to get the electricity out of you get a production of electricity with a better magnet. And so that's why this element, these rare earth elements like neodymium, are sought after at the moment. And where do they find that? They usually find it in special situations in ore deposits that are unique. It's often in uranium deposits, but the biggest producer of rare earth metals at the moment is China. They have over 90% of the market, which is a problem. And the US government, of course, is interested in companies exploring for it. There is a mine that went out of production in California that's come back in to production because of the prices have skyrocketed. That's in Mountain Pass, and it's usually in very unique situations, and that's a whole different realm in talking about where ore deposits occur and why. But we'll touch on that a little bit when I talk about radio halos, actually, on Wednesday, tomorrow. So, how do we go about the process? And this is fleshing out a little bit more of what I just dealt with very briefly yesterday. A rock is chemically tested for the parent and daughter atoms. If the rate of radioactive decay has remained constant at today's measured rate, then we can calculate how long it has taken for the measured amount of daughter atoms to be derived from parent atoms, and that time is regarded as the rock's age. And that, of course, involves assumptions. And let's step through this again a little bit more slowly, but it's really that simple as this. It's a very good analogy. The red atoms or red sand grains in the top bowl of the glass, hourglass, is analogous. The red sand grains are analogous to the pair atoms. The radioactive decay, the falling, is analogous to it. And then you get the green sand grains at the bottom in the bottom glass bowl. And we know that if we start with no green sand grains down the bottom, but all the red sand grains up here, then it's an hourglass. It takes an hour for the red atoms to fall and become green sand grains. And so this is the analogous process. Now, you immediately recognise that this has already been calibrated. You buy it as an hourglass. It's already been tested by an external, objective way of checking this clock. But of course, what external standard or objective way do we have of assessing these radioactive clocks in the rocks? We don't. And so that means the assumptions are very much an issue. So we start with the sand grains at the top bowl. It takes 1 hour for the red sand grains to fall to the bottom to become green. So we can actually chemically test. In other words, we do an eyeballing of the situation. We can look at how many red sand grains there are at the top, but more importantly, how many are green are down the bottom. And so you know that if a quarter of the sand grains are down the bottom, it's been 15 minutes that your clock has been ticking. It's that simple. In other words, you can back calculate how long ago the clock started. And so it's the same with the rocks. You measure the amount of daughter atoms, and then you can back calculate. Well, okay, if there are no daughter atoms to begin with in the rock, then we know the rate of decay. It's taken X years to produce Y number of daughter atoms. Therefore, that's when the rock was formed, and that's the age of the rock. It's not that mysterious at all. So, as again, it doesn't hurt to keep revising this. The rate of radioactive decay, that is the falling, has remained constant then it can be calculated how long ago, how long it took for the measured amount of green atoms, the daughter atoms, to accumulate from the red atoms, the red sand grains at the top. That's how long the hourglass has been operating. But when we use that hourglass clock, we have three crucial assumptions. And as I said before, we have an objective. The hourglass clock has been objectively tested and checked. And so those assumptions are not so critical, but they are when we're looking at the rocks with these radioactive dating methods. When there's been no objective external standard, then these assumptions become very crucial. And there are three crucial assumptions that are always involved with this system, and let's go over them. Assumption number one, the amount of parent and daughter atoms at the beginning when the rock formed, that is, the initial conditions, must be known. You must know the initial conditions, or you have to assume them. And so, for example, it is assumed that when a volcanic rock forms, such as a basalt, then it will have no argon atoms in it. And that the argon atoms that we measured in today have all been derived from radioactive decay of potassium in the rock since the rock formed. And so we have to assume that there were no green atoms in the bottom of the glass bowl at the beginning, or there was a known amount, and that is that there was no inheritance. In other words, the rock didn't already form with inherited green atoms or daughter atoms in it. And of course that requires an observer. Were there observers there when the rock formed? Well, usually no, but an example I'm going to give you, yes there were. And we find that the method doesn't work when there is an observer. So if when the method doesn't work when there is an observer, doesn't it beg the question is, well, when there is no observer, can we be certain that the method also works there as well? We'll come to that momentarily. Assumption number two, all the daughter atoms measured today must have only been derived by in situ radioactive decay of the parent atoms. You know what the word in situ means, in place. And you have to therefore have a closed system. It's like I say to people, while you start your hourglass clock in the kitchen, and while you're out of the room, your mischievous 10-year-old comes up and lifts up the lids and puts more red sand grains in, and you come back and do an estimation. Well, your clock's going to fail, isn't it? Because it's been contaminated, it's been interfered with. And so the geologist has to assume that his rock's been sitting out there for millions of years and it hasn't been contaminated, which is absurd. The reason why it's absurd, and here's the summary. First of all, it requires an observer through all those millions of years to make sure that there's been no contamination. But most people don't realise it's only when you get involved in geological exploration with mining companies and you do a drill hole, you start drilling down through the rocks from the surface, and then you dig down in a mine, put a shaft down. Most people think that rocks at the surface look pretty fresh. You can tell a weathered rock from a fresh rock. Well, it might surprise you that even the so-called fresh-looking rocks in outcrops are already affected by weathering. And the weathering effects can go down as deep as 500 feet. So that means that the samples you collect at the surface, which is primarily what is done for radioactive dating of rocks, already have the effects of weathering involved in them. So they've already potentially been contaminated because groundwaters bring in sulfur from the air, mixed with water, sulfuric acid, acid rain. You're going to affect the minerals in the rocks. And any geologist who looks at a rock sample under a microscope, at the microscopic scale, you can start to see those effects. So that's a problem. And assumption number three, the radioactive decay rate must have been constant at today's measured rate. That's an obvious thing. What happens, of course, if your mischievous 10-year-old puts a few drops of water inside the glass bowl, what's that going to clog up your grains and the rate of falling is going to change. If the radioactive decay rate has changed in the past, then the clock can't be used as an accurate timepiece. And so, again, this requires an observer. Has a geologist been there for millions of years watching and measuring? No, we've only measured these decay rates in the laboratory in the last 80 years. And I wanted to delve into this issue, so I actually did a series of papers that are available on our Answers in Genesis website at our Answers Research Journal. It's online published, so it's free, you don't have to subscribe. And there's a whole series of papers on reviewing how the methods, how the different decay rates were determined for the different isotopes and the problems that have resulted, that have cropped up as a result of doing that. So it's by no means even certain in the last 80 years that the decay rates have been constant. There's hints in some of those measurements that it's only because they've assumed they had to be constant that they've smoothed out the results. So we can sum up these three crucial assumptions. Number one, all the daughter atoms derive from parent atoms, or we know the initial conditions. Number two, no other processes affected the parent-daughter relationship. And number three, constant decay rates. I want to show you that none of these assumptions are provable. Why? Because the past cannot be observed and measured and can't be tested. We weren't there in the past to be dogmatically assertive that these assumptions are all proven and correct. But the reality is that these assumptions are not even reasonable. Everyday experience, just like I explained to you about weathering and what rainfall does and what groundwaters do, how deep weathering goes, shows you that these assumptions are not even reasonable. And we know that daughter atoms may be inherited when the rock forms, as I'll show, and contamination subsequently is common. Now, I want you to understand the quality. I'm not disputing the quality of the chemical analyses. If you're even aware of these laboratories that do this work, you will know that it costs hundreds of thousands of dollars for the equipment in well-constructed laboratories, ultra-clean rooms for preparation. So you're talking about an investment of millions of dollars to set up one of these laboratories. And so there's no question that the state-of-the-art laboratories do wonderful chemical analyses. I can send the same sample, splits of the same sample, to 3 different laboratories, and I'll guarantee that they'll each hit about the same the same target with the chemical analyses that they produced. But it's the interpretation of those chemical analyses. You've got to then take those chemical analyses and plug them into an equation for determining the age, and that equation is built around these 3 assumptions. So it's the assumptions that we're questioning that give the interpretation, not the quality of the chemical analysis, and that's a good point to emphasise. They claim that they can overcome the problem of assumption number 1, the initial conditions, by using the isochron method. Now, I don't have time to go into great detail about that, but the normal model age, what is called a model age, is based on using 1 sample of a rock. You get the chemical analysis and you plug it into the model age equation. And so potassium argon ages are usually model age equations, model ages. But you also, in the isochron method, you use multiple samples. And the idea is that in the same outcrop, same rock unit, different outcrops might have different amounts of potassium in them. And, potassium, it depends on the amount of particular minerals. How much biotite's in the granite, or how much potassium feldspar is in the granite. So different samples from the same rock unit will have different amounts of potassium, which means, in theory, they should have different amounts of argon in them as well. And so when you plot that as potassium versus argon, you're going to have a spread of data points, and the line of best fit is the isochron point, isochron line, which gives you the isochron age based on the isochron age equation, which is the slope of that line. But because you've got multiple samples and you've actually, the wider the range of values of the parents and daughter will give you a better spread on your graph, which will give you better statistics on your line of fit. And so the isochron age, and it doesn't require knowing the initial conditions. In fact, you can effectively, they claim, work out the initial conditions by projecting the isochron line back to 0. So it seems to overcome the assumption number 1, and I say seems very deliberately because it really doesn't overcome that problem. Assumption number 2 is usually say we can show that where that's been violated because we can detect the contamination. In the case of the isochron method, any points that don't plot on the isochron line are assumed to be due to contamination. But how do you know that the dots, the samples that don't plot on the line, they might actually be the true age? The ones that line up on the isochron might be the contamination because it might be a mixing line. And I'll show you an example of that later on. It might be where you've distributed the composition based on the groundwater's distributing it and you've got a mixing line. So that doesn't help you. Just because you don't, and also just because you don't detect contamination doesn't mean it isn't present. I'm going to show you a beautiful isochron later, but it's totally meaningless because it's a mixing line. So let's go through these. Assumption number 1, no inheritance. Assumption number 2, no contamination. Assumption number 3, constant decay rate. So let's illustrate this. That's the best way with specific examples. Dr. Austin talked about Mount St. Helens yesterday. He didn't tell you, though, the rest of the story. After the main eruption, of course, which blew out the top of the mountain, in the exposed crater, lavas continue to ooze out and start to build a new lava dome. And we watched it grew. We knew when each of the lavas flowed out. And so Dr. Austin with Dr. Ken Cumming there from ICR, they went up into the crater of Mount St. Helens. There was a lava flow up there that we knew had flowed out in 1986. We actually observed when this rock formed. And so when it was sampled in 1996, it was 10 years old. Okay? So we knew the real-time age of this rock. It had crystallised from the lava in 1986, sampled in 1996 and sent to the laboratory in 1996, so we knew the true age. And here's the results that were obtained. On a rock that had a real age of 10 years, the potassium-argon model ages varied from the whole rock from 0.35 million years. We separated different minerals and dated the minerals separately. And so in a pyroxene concentrate, we got an age up to 2.8 million years for a rock that was only 10 years old. And the answer was obvious. Well, it had inherited excess argon. In other words, there was more argon in the rock than had come from radioactive decay. That's what it's meant. The star symbol is radiogenic or radioactive decay derived argon-40, because actually there's argon-40 in the atmosphere as well. And so you've got to factor that in when you do your chemical analysis and interpret it. That's a whole different story. So, where did the extra argon come from? Well, if you test the volcanic gases, primarily steam, but if you test the volcanic gases coming in a volcano, they can contain argon-40, because that's how the atmosphere gets argon-40. So in other words, when the lava cools, what's it going to do? It's going to trap in it some of these gases that are coming up in the volcano, which include argon-40, so it's actually going to inherit argon-40 when the lava forms. So if you come along and then assume that when you measure all the argon-40 in the rock, it came from radioactive decay from potassium, dong, you're going to get the wrong answer, because you haven't factored in this inheritance. And so that is well known in the literature. Look at these results here. From a Hawaiian lava, which we saw the eruption in 1800 and 1801, you get potassium argon ages up to 1.4 to 1.6 million years old. This is all from the literature. Mount Etna, the two different eruptions there, and you can see the ages that arrive. Mount Lassen in California, and also Sunset Crater in Arizona. That's the youngest volcanic eruption in Arizona, and you can see that all of these results derive from inheritance of excess argon. It's all in the literature. It's been well documented for 50, 60 years in the literature that this is a common problem with recent lavas. Recent historic lavas will always give you, will invariably give you, many of them will give you excess argon and therefore wrong potassium argon ages. So as I said before, it begs the question, if this is what we find with recent lava flows, what does it mean with regard to the same method being used on ancient lava flows? Wouldn't they similarly have also inherited excess argon? So therefore, can we believe those ages as well? Here's another situation where in Hawaii they tested what happens when the lava erupts underwater. The outer skin of the lava, lobe of lava that's going out there is going to quickly cool, and it's going to mushroom like a pillow. The outer surface will cool very rapidly, while the inside it takes a little bit longer. And so that will affect how much argon can get trapped in the rock. And so here they did an analysis from the rim of one of these pillows, or these lavas that had cooled rapidly underwater, and they looked at the date as you went in and so the date changed. These are centimetres. So for translations purposes, 2.5 centimetres is an inch. So we're talking about here 4 inches into the rock, this lava flow, cooled lava flow. And so as you get into this pillow, the rock actually gets younger, because what happened is at the outer skin, it cooled so rapidly, it was able to quickly locked in all the argon that was available, whereas inside, as it cooled more slowly, it didn't lock in as much helium. So here's a table of, and that's already published. That's out of the first of the rate volumes, the 2000 volume, which was a summary of the state of the art of the situation that we were investigating in that project. And here's the references out of where that came out of the literature. More examples, 10 Zaire diamonds. Actually, Zaire is no longer the name of a country. It's the Congo Republic. But 10 diamonds yielded a potassium argon isochron age of around 6 billion years. Well, they immediately recognised that can't be true, because how can diamonds that come from inside the Earth be older than the Earth itself? The Earth is claimed to be 4.5 billion years old. And so they immediately knew that these diamonds had somehow inherited excess argon, and sure enough, you can find the fluid inclusions, little fluid bubbles inside these diamonds, and you analyse those and you find the excess argon there. So, you know, when we can nail it down, we can find out that this is a recurring problem no matter what the supposed age of the rock is. So obviously these diamonds inherited excess argon. Two volcanic centres 100 miles apart in the East African Rift Valley, the lavas were supposed to be less than 1 million years old. We knew that was known because of the interrelationships with other rocks that they were interlayered with away from the eruption centres. But these two volcanic centres 100 miles apart, samples from them plotted on a rubidium isochron that gave an age of 773 million years. So obviously they knew that this was a problem because these were recent lavas. But a recurring problem, 14 different recent ocean island basalts, that is basalts on islands in the oceans that have recently erupted, yield a rubidium strontium isochron age of nearly 2 billion years. And the same is true with lead. Lead ages, just to bring you up to speed, a lead age is by contrasting the lead derived from uranium-238 with the lead derived from uranium-235. It's supposed to be the premier way of dating using the uranium-lead dating method. And so you can see here all the names of the different islands in the Azores, the Canaries, the Easter Island, you're familiar, Hawaiian Islands. The lead ages are around 1 to 2 billion years. And this has been known for over 50 years in the literature as the lead isotope paradox. Why is it these recent lava flows give such old ages? And the answer is that they inherited from their mantle sources. So it's to do with the chemistry of the mantle, not the age of the rock. And that's well known in the literature. So if that's the case with the recent lava flows, what does it tell us about the ancient lava flows? And we used this example yesterday. We've got at the top of the Grand Canyon these Uinkaret Plateau Basalts. This is the Uinkaret Plateau, the north rim of the Grand Canyon in that area is called that. You've got these domes, craters. In fact, there's something like 180 of them. They're all lined up along fault zones, cracks where the lavas came up and erupted. And some of these, the lavas flowed down into the Grand Canyon, blocked the Colorado River, and dammed up the river that then broke through. And so these are very young. In fact, there's some evidence that the most recent of these lavas were actually witnessed by the Native Americans. So that means they're post-Babel. So here they are. Here's Vulcan's throne. Here's the Colorado River. The lava's flowed down here. By the way, the best rapid on the river, which is the fastest navigable rapid in North America, is right here. It's called Lava Falls Rapid. 19 seconds of sheer terror. Particularly if they're letting water out of the Glen Canyon Dam at a rate of knots, it's really a raging torrent. So here the lava's filled in whole side canyons. So down the bottom of the canyon, we've got these Cardenas basalt lavas. They're interbedded with these Precambrian sediments, which I'm going to talk a bit more about on Thursday morning. But these are pre-flood rocks. Here's the beginning of the flood sequence, which the horizontal layers that are fossil bearing making up the canyon. And so these are ancient by anyone's determination, and very much older than these more recent lava flows that were erupted after the canyon formed. So here are these Cardenas basalt lavas, and so what they both give rubidium strontium isochron ages that are very similar. And why is that? Well, here's the spread of Uinkaret Plateau Basalt ages, which is the correct age. I said that yesterday. Obviously, this is the ones that are closest. Why are these so high? Well, the Cardenas and the Uinkaret Plateau basalts, they're both basalts. They didn't come from just beneath the Grand Canyon. They came from deeper down in the upper mantle because the continental crust is granitic in composition. The upper mantle is basaltic. So the melting of the upper mantle produced these lavas. And so the answer is that these recent basalts inherited their old, quote, ages from the mantle source beneath the Grand Canyon. The Cardenas basalt had previously come from the same mantle source and so it would yield the same rubidium strontium age. I put age in quotation marks because these cannot be the true or real ages. They are simply an artefact of the mantle source or the mantle chemistry. And why can I say that with good authority? Because that's the explanation for why the recent lava flows on those ocean islands give billions of years ages. The conventional community accepts that it's because of the inheritance from the mantle source. Well, why doesn't it apply here also in the Grand Canyon? Well, because they don't want it to apply the same. But the evidence shows that it is the same methodology that we should, and reasoning that we should argue for why you get these artificially old ages. It's simply because of the chemistry of the source. So, we've quickly seen that assumption number one, no inheritance, has been violated because there is common inheritance in many of these examples that we've shown. We've actually documented that inheritance is a major factor. And just because we don't detect inheritance doesn't mean that it isn't already there. Yes?
Are those exceptions as far as, do we have 100 ones that we have seen that actually give a date that they would say, but we got 5 here that give a way too old one, or is that pretty standard?
Well, no one has really assessed in the literature, a proportion. What we do know is that whenever we observe, we know the true age of the rock, the method fails. And so that should, 100% of the time.
So 100% of the time,
yeah.
we know the age.
Yes.
Fails.
Yes.
Okay.
And so that then begs the question, well, why should we assume that it works when we don't have observational evidence of its true age? So the next issue is contamination. Let's go to the North Island of New Zealand. Mount Narahoi was made famous as Mount Doom in the Lord of the Rings series. Okay, and here it is in the foreground. Mount Ruapehu is in the background. It's still active. Mount Narahoi has been dormant since 1975, but prior to that, it was New Zealand's most active volcano during settlement by the British. And here it is up close and personal, and you can see that different colours. Some of these have been more overgrown than others. That's why we can tell the ages. In fact, because of observations of these lava flows, we know the day, the month and the year of each of the lava flows that came down the mountain. In fact, they've all been well documented. And so it's very easy to go in using the map, using your observations to actually recognise which lava flow dates from which eruption. So it was possible, therefore, to go in and get samples, which I did. And so a lot of these examples a number of these examples I'm going to give you are actually our own research. And people say, did we set up our own laboratory? No, we didn't do that. We used the conventional laboratories. Why? Because if we'd set up our own laboratory, people wouldn't believe the results that we produced. And that's still valid. I think we have to recognise that. Work within the system to show the problems. So, for lava flows that were date from 1949, 1954 and 1975, I got potassium argon model ages up to 3.5 million years, obviously due to inheritance of argon-40. We get a rubidium strontium isochron age of 133 million years, although notice that went the wrong way. Hang on, go back. Okay. Notice that there was a large error margin there. And this is due to contamination. It's well documented in the literature that there is if you use these 3 N-member isotopes, you can calculate how much contamination there was from the fact that an andesite, if you're familiar with the literature, a basalt has low amount of silica in it, and it's a lava. Most people don't realise that the underground equivalent is called a gabbro. It's not a granite. even though most black granite bench tops are actually gabbro, they're not granite. The other end of the spectrum is a granite, which has a lot more silica in it, different chemistry. Its lava equivalent is called rhyolite, okay? And between them, there's a spectrum. And so a basalt that's been contaminated is called an andesite. And if it's contaminated a little bit more, it's a dacite. So Mount St Helens was a dacite eruption, and then rhyolite. As you go from basalt to rhyolite, you get more explosive eruptions. Why? Because they're more viscous, and therefore the steam builds up and you get much more of an explosion. That's why Mount St Helens was explosive compared to eruptions in Hawaii. They're basalt. Where does the name andesite come from? The Andes Mountains. And so what happens is you have a basalt magma coming from the mantle. It comes up through the crust. It gets contaminated. In this case, 5 to 10% contamination. And that contamination changes the composition to an andesite. As a consequence of that contamination, it's affected these radioisotope systems. They become contaminated. Here's some more examples of contamination. A granitic rock in South Africa yielded a lead, and samarium neodymium age of 2,915 million years, but a rubidium strontium isochron from minerals within the rock yielded an age of 2,023 million years. Quite a significant difference. How can the minerals in the rock date much younger than the whole rock being crushed? So a whole rock age is when you crush the whole rock and date it. A mineral age is when you separate the minerals and date them. 1 grain of albite, which is a feldspar mineral in the rock, yielded rubidium strontium ages of 5.8 billion years, or 5,852 million years at its outer edge, and its core 3 billion, or 3,067 million years. So it tells you that things are going on when these rocks crystallise and the minerals crystallise, locking in the different elements as a result of what's available in the magma. And so again, it's contamination. It's to do what's around at the time the rock forms. Here's another example of what can happen. On this side of the screen, we've got a granite that's supposedly 54 million years old. It's intruded into Precambrian schists, metamorphics, that's supposedly 1,375 million years old. And when we do some dating, we find that the dates increase as you get away from the granite or decrease as you get to the granite. And that's been due to the granite's heat and also fluids, hot water coming out of the granite. And so here's the graph. Here's that boundary there between the granite. It's that boundary there. In the graph is here. Okay. On this scale is the apparent age, and here's the distance. So we're talking a kilometre here. We're talking 2 miles out. By 2 miles out, you're getting close to the supposed true age of the rock out here, the host rock. But as you go towards the granite, the ages come all the way down close to the age of the granite. These are the potassium, argon, rubidium, strontium, using different minerals. If we also look at it with the uranium ages, the scale is different. Now we're only down to 50 feet. It hasn't been perturbed as much by distance, but it shows you the heat and the fluids coming out of the granite can contaminate and therefore change these ages. Not because it's changed the decay rate, but it's changed the parent-daughter relationship. It's interfered with the concentrations of these isotopes. And so if a little bit of heat and water can do that, then what's happening out there in the outcrops that are being weathered by rainfall and groundwaters? Here's another situation. Here we've got the granite in pink, okay, and within it we've got these zircon grains. Zircon is zirconium silicate. The metal zirconium, combined with the silicate molecule. And uranium has a similar atomic radius, ionic radius, and it will substitute into the lattice with some of those zircon atoms. And zircon, therefore, is a very hard mineral, and it's become the showpiece for uranium-lead dating of rocks. And yet here's a situation where we can show these zircon grains, they're claimed to be inherited. Why? In many granites. Why? Well, we get zircon ages, uranium-lead ages up to 1753 million years in a Himalayan granite supposedly 21 million years old. How can the zircon grains be hundreds of millions, nay, billions of years older than the rock itself? Well, the argument is, oh, well, the rock has been inherited these zircons. It came from when the magma formed, when previous rocks melted to produce this granite magma. The zircons stayed whole, they didn't melt because they are high temperature, and they were inherited in the rock. Well, that's only an arbitrary explanation because we weren't there to see it happen. Zircons also crystallise from a magma. And it's not as if it's a lone example. Here's another example, a granite in southeastern Australia, supposedly 426 million years old based on rubidium-strontium dating, has zircons within it with ages up to 3.5 billion years. And another example here in New Zealand, a granite supposedly 370 million years old, has zircon ages up to 1638 million years old. But if that isn't bad enough, look at this example where we got supposed monazite is a calcium phosphate mineral where you get substitution of uranium and thorium into it. And a Himalayan granite supposedly 20 million years old has zircon grains with uranium-lead ages up to 1483 million years, but also has monazite grains with uranium-lead ages of minus 97 million years. Well, what does that mean? The minus 97 million years means the monazite grains haven't yet formed. But we see them in the rock. So you see, how can this be a question of inheritance? You can't inherit a mineral grain before it forms. It formed in the rock, but it yields a minus 97 million year age. So how can we be sure that these zircon grains were also inherited? No. It tells you that what happens is that when the rock crystallises, these elements are partitioned into the different minerals that crystallise from the magma. A magma is a molten liquid. As it crystallises, different elements get partitioned into the different minerals that crystallise. And so you've got unequal distribution of lead in relation to uranium. Because then you come along and you measure the uranium-lead relationship. If you assume that all the lead came from the uranium, by radioactive decay you're wrong, because it's to do with how much lead was partitioned into these minerals when they formed. You get my drift? The minerals inherited more lead than they should have. Here's another example. We have two grains side by side. This line here is the edge between these grains. And these stars represent argon-argon analyses. The methodology is, the technical methodology has become so sophisticated, we can produce an electron beam or an ion beam that's 1 micron in diameter and zap the surface of a mineral grain to obtain an age on a spot 1 micron wide, which means you can actually, in this instance, you can date different spots on this grain at the microscopic scale. So taking this boundary here, which is the edge between these two biotite grains, biotite is the black mica that's common in granites. And what do we get? Here's that boundary here. Remember, each of those stars represents an analysis point, or they're numbered, and so they're numbered in this one here. So in grain B, this is analysis 2, 3, 4, 5 to 12, like we had before. The distance is only 100 microns in from the edge to the centre in here. Notice that the age, the argon age drops from 515 million years at the edge down to 160 million years inside. And that's only a distance of 100 microns. I mean, which is the true age of this mineral grain? Does it mean that the edge inherited more argon? Well, these are unanswered questions, but obviously something's going on here. Did argon, it's not as if it leached out, because you'd expect a lower age at the edge. So it's a real problem. Here's another example. Remember I said you can focus a beam 1 micron in diameter, so that you can look at, in this instance, crystal faces. They took crystals of badallite, which is zirconium oxide, from the Palabora mine in South Africa, and they set up in the machine that they could rotate the crystal. So that as they rotated it, you could actually put the beam on different faces, but at different angles to the face. That's at right angles. This is an oblique angle. This is close to right angles. This is more an oblique, okay? And so you can plot the angle versus the age. And so what do we get? Here's the angles, here's the ages. As you rotate these crystals, you get variations of several hundred million years depending on the angle of the beam to the face. So what does that tell you about the ages? They're meaningless, because it depends on the angle of your beam to your mineral. So when you actually get a rock where you've got a flat surface with all those different grains in that you're analysing, how do you know the angle of the beam to the crystal? Because you've cut your rock to get a flat surface, you don't know the angle. So how do you know that you're getting the correct ages? So numerous examples show that other processes have affected the parent-daughter relationship. So assumption number 2 is violated by contamination. What about number 3? It is insisted that assumption number 3, constant decay rates, is universally true in the conventional literature. That's the sacrosanct assumption. Why? Because the resultant ages give us the millions of years that are needed for evolution to be true. That's why this age issue matters. As soon as you show that the age of the earth is young, then there's no time for evolution. And the Bible has to be true, and there has to be a creator, and therefore we're all sinners in need of repentance. That's what they fight against. It's ultimately a spiritual issue, this time question. But why should radioactive decay rates have always been constant at today's measured rates? Has sedimentation always been at the slow rates we see today? No, during the flood they were catastrophic. So if you had catastrophic sedimentation and erosion, catastrophic plate tectonics, why not catastrophic radioactive decay during the flood, for example? That would be a logical expectation. Well, here are the 4 major methods again that are used: potassium to argon, rubidium, strontium, uranium to lead, samarium, neodymium. Now, most geologists usually only use 1 or 2 of these methods on the same rock, because it's assumed that all methods should ideally yield you the same age. Why? Well, as I said yesterday, it's like having 4 different hourglass clocks on the bench here, but put different sized red sand grains in the top. They'll all still fall to the bottom to give you green sand grains, but the clocks should all tick for 1 hour, in spite of the different sizes of the sand grains. Well, it's true with radiometric clocks. In theory, no matter which clock you use on a given rock, it should give you the same age. So we decided we're going to test this, because there were hints in the literature that this was not true. And so we decided that we would use all 4 methods on the same rocks, and would use multiple samples. We'd use the superior isochron method, so it was harder for our opponents to argue against us. And that would help our cause. And so we went to the Grand Canyon. Those were the days when it was easier to get a sampling permit. And we decided to look for different rock units that were datable. And here we have what we call a diabase sill. This is where a basaltic magma hasn't reached it all the way to the surface, and instead it moves out laterally underground between two other rock units. We call it a sill, and the resultant rock is a diabase. It's a basalt that's got larger crystals, similar composition. It's given a different name. It's called a diabase, and it's right here at Hants Rapids. Here's another example down at Bass Rapids. We've got this one is much, much thicker. In fact, this was ideal because see this pink rock at the top? That's actually a granitic rock, but it's part of this same sill. What happened, as the magma came in, it cooled slowly enough that the denser, heavier grains of olivine sank to the bottom, and the lighter grains of potassium feldspar rose to the top. And so there's a chemical differentiation of the rock through its thickness, which means there's a spread of chemistry which will give you a better isochron, because as I said before, the broader the range of chemistry in your samples, the better your statistics. And so that was ideal. And so here's the Bass Rapids diabase sill down here. That's right down deep in the canyon. It's pre-Cambrian. And so here's the results that we got. Potassium argon, 841.5 million years. Rubidium strontium, 1,060 million years. Lead, 1,250 million years. Samarium neodymium, 1,379 million years, which is the correct answer. What about E, none of the above? How would we know if there wasn't an observer there? And the answer is they're probably all wrong. But notice that the potassium and rubidium are younger than the lead and samarium, and the potassium is younger than the rubidium. Watch that, because we move on to the next example. The Cardenas basalt lava flows that we talked about before erupted onto the surface, and there's a succession of about 6 or 7 of these lava flows. We can go in and sample them, and here's a boundary between two of these flows. There's a younger looking Dr. Steve Austin, and there's where they are in the canyon down here in the pre-Cambrian. And here's the results. Potassium argon, 516 million years, the youngest. Rubidium strontium, 1,111 million years, the second youngest. Potassium is younger than rubidium. And samarium neodymium, 1,508 million years, which is the correct one. How would we know without an observer? Now I want you to notice not only there's a pattern here in the ages, but notice that the samarium is 3 times the size of the potassium age. I mean, how accurate is that when you get a 300% difference in the ages? Not very accurate at all. Down the bottom of the Grand Canyon we have where basalt lava flows under temperature and pressure metamorphosed into what we call an amphibolite. It comes from the major mineral in the rock called an amphibole, and so the rock is called an amphibolite. And they're black looking rocks like this, and you can actually see here's the boundary between original lava flows. And here they are, they're down in the so-called metamorphic complex, which has been subdivided now into different names. Vishnu is just one of the names used down there in the metamorphic rocks, but they're really early on in the history of the canyon. And we'll talk about where this fits into Earth history from a biblical perspective on Thursday morning. Here's the results. Rubidium, 1,240 million years. Lead, 1,883 million years. Samarium, 1,655 million years. Notice, again, rubidium is younger. None of the above. Which one is correct? How will we know without an observer? Well, example number 4, Elves Chasm granodiorite, regarded as the oldest rock in the Grand Canyon, traditionally 1.84, 1.85 billion years. And what results did we obtain on this rock? Here it is. We're right down here in a relative sense. Rubidium, 1,512 million years. Lead, 1,933 million years. Samarium, 1,664 million years. Which is the correct age? How we know without an observer? By the way, all of this is documented in the 2nd volume of the RATE project, the 2005 volume. And again, notice the systematic pattern. Rubidium is the youngest. The beta decayers give younger ages. And so once you know there's a pattern, that's one of the things I'm interested in when I'm looking at the big picture. Well, I want to get a heap of data. You know, some people like 1 or 2 pieces of data. I like thousands or millions of data, and then I go looking for patterns, and then I have to say to myself, what do these patterns mean? But not in context of the conventional paradigm, but in terms of the biblical view of Earth history. And so if there's something systematic going on here, what could cause it? Well, the answer is each of these methods disagree, but they each refer to a unique once-only geologic event. The formation of a sill, the metamorphism of the lavas, the volcanic eruption or the crystallisation of the ground. That was a unique once-only event when the rock formed. So if these clocks were accurate, all ticking at the same rates as they are measured today, they should have all given the same age. So if they give you different ages, what does that tell you? They may have been ticking at different rates in the past and different faster rates. Why do I say that? Well, if you look at the Cardenas basalt, while the potassium clock ticked through, you've got a real time period between when the rock formed and when we measure it today. That's the real time period. During that same real time period, the potassium clock ticked through 516 million years, the rubidium clock ticked through 1,111 million years, and the Sumerian clock ticked through 1,588 million years. So in other words, they were ticking at different faster rates. Why were they ticking at different faster rates? Because one, they were alpha decayers and beta decayers, so there has to be some difference between that. And also, they had different atomic weights. Potassium is the smallest atomic weight. It gives you the youngest ages. So we lined it up and you could see there was a pattern according to atomic weight. There was also a pattern according to the length of the present decay rate. The shortest decay rate in the present is potassium, gave the younger ages. The larger decay rates, the slower decay rates, that is, gave bigger ages in the past because they were accelerated by a greater amount. So that invariably tells us that the clocks were speeded up during some catastrophic event during the past. And so, therefore, if the decay rate was accelerated in the past, if we assume a constant rate of decay, then our clocks are not going to give us accurate absolute ages. Absolute ages. Now, do isochrons always represent ages? You know, these straight lines where we've got multiple samples and you get the slope of the line gives you the age. Well, the isochrons are straight sloping lines based on chemical analyses of 4 or more different samples from the same rock unit. By the way, I should have added that when we did the dating in the Grand Canyon, we used more than 4 or 5 samples. The Bass Rapids Diabase Sill was 11 samples. The amphibolites were over 20 samples. So that really improves the statistics of your isochron. The slope of the isochron is claimed to represent the age of the Earth, the age of the rock, but do those straight lines always represent ages? Well, let me give you an example. This was the area where I did my PhD thesis research. And the Koongarra, this is the, if you ever saw the movie Crocodile Dundee, this is Crocodile Dundee country. It's up in what we call the Alligator Rivers province. It's the name of the rivers, and yes, they're not alligators, they're crocodiles. They're saltwater crocodiles and they're man-eaters. And this is now a national park and a World Heritage listed area. But in the late 1960s, uranium was discovered. And it put the Americans out of business because these were high-grade uranium deposits. And one of those that was discovered was the Koongarra Uranium Deposit. It hasn't been mined yet because it's in a national park, and the land was also handed back to the traditional owners, the Aboriginals, the native Australians. And so I did my PhD work there. Here's a very famous location. This is a lake a pond that's, you have the wet season in the tropics where you get a lot of flooding, and then it dries out and you get these ponds. And this is a famous cliff face that's very popular, very scenic. Here's an aerial view of the uranium deposit. This is the road that was put in, and this is the drilling grid. The uranium deposit is in this direction here, and we drilled through cross sections here to obtain, to prove up the uranium deposit. This is what the uranium ore looks like. The black is pitch blende or uraninite, and it's been altered with oxidation by fluids. You get casolite is orange, it's uranyl silicate, glaustite is the yellow one. And so a friend of mine, I was involved in this project, and we wanted to use what was in the ground as an analogue for how we would explore in other areas to find other deposits. Okay, so we're developing exploration techniques. We decided to look at uranium isotopes in soils. So we took soil samples from over the uranium deposit, and sure enough, you got a signature from uranium decay, a lot of lead from uranium decay. Then we looked at soil side of a mountain in a different rock unit. And we got all these soil samples and we plotted them, and lo and behold, they plotted an isochron line. But these were soil samples. In actual fact, the closer to the uranium mineralisation, the closer we got to the signature from the ore deposit. So this was only an apparent isochron, it was actually a mixing line. It had nothing to do with the age of the soils. It had to do with the amount of uranium, and therefore the amount of lead that was in these soils by groundwaters moving the material, moving these isotopes around. So just because you get a lovely isochron, and this had wonderful statistics, and we published this in the open conventional literature. So you saw, I can talk about research that we've actually done. The guys that were working with me on this work with the government research agency called the CSIRO in Australia. Here's another example from the literature where you can take the strontium and neodymium isotopes in granites in southeastern Australia and show that they sit along a mixing line, which is a mixing of a mantle component in the granites and a crustal component. So, this has nothing to do with the ages of the rocks, and yet strontium and neodymium are the end members of two radioactive decay clocks that are used to date these granites. And yet we can show that these daughters actually plot along a mixing line. So, assumption number 3 is violated by accelerated decay rates and mixing. So where does this lead us? The 3 crucial assumptions of which radioactive dating methods depend have been all shown to be unsustainable and unreasonable. Inheritance and contamination in rocks are common when they can be detected, which begs the question as to how can we be sure that they are not also common in rocks of unknown age, inheritance and contamination. And the answer is, of course, we can't be sure. If there wasn't an observer to test when the rock was formed, how can we be sure? Decay rates have been shown not to have been constant, but have been accelerated during some past catastrophic event. And I might add here as a side note, if you're familiar with the results of the RATE project, the Radioisotopes and Age of the Earth project, there were several lines of evidence that converged on that conclusion. It wasn't just these discordant, what we call discordant or disagreeing radioactive ages that I've shown you in this presentation, but there was also the helium leakage, there was also fission tracks, there was also radio halos that I'll come back to on tomorrow afternoon, all show that decay rates had to have been accelerated in the past. So it's not just based on the examples that I've given you here this morning, it's based on several lines of evidence that converged on the same conclusion. And we've shown that apparent isochrons can also be mixing lines. Thus, all the radioactive dating methods are subject to the same uncertainties. Inheritance, contamination and non-constant decay rates make all the radioactive decay methods totally unreliable. Therefore, they cannot provide for us absolute ages for rocks and meteorites. Implications, however, come from out of this. And stay with me. The resultant millions of years ages, though unreliable and highly inflated compared to the biblical time scale frame, can still give us a relative order of relative ages in the rock units data. They still match the relative order. You know, all those samples from the Grand Canyon come from what we call the Precambrian, and they all yielded Precambrian ages, apart from the 516 million year age for the potassium argon age for the Cardenas basalt. In other words, they match. Well, that's because the time scale was built from radioactive ages, but you still hit the target in terms of where in the geologic column the samples come from. And so that gives you a clue that even though the absolute ages are wrong, you can still use the methodology. When you have an unknown rock, you can test it for radioactive decay ages, and that will help you give a relative age of where it fits in the geologic column, or where it fits in the order of Earth history from a biblical perspective. So here on this graph we can see that many of the accepted radioisotope ages do in fact match the relative order of the strata. Here's where they match along this line here. You've got lots of outliers, sure, but you've got a lot that match. So why would that be important? So where the relative ages of strata are not evident or cannot be determined for geologic relations, then radioisotope ages might be a relative guide. Why do I say that? Well, as I said, in our RATE project, we found 5 independent lines of evidence: the systematic discordant radioisotope ages, helium diffusion or leakage, radiohalos, fission tracks, and radiocarbon. I didn't mention before, but we'll come back to that in the next session. That demonstrate radioactive decay rates must have been grossly accelerated during one or more recent catastrophic geologic events, especially the flood. So, if radioactive decay was grossly accelerated during the flood, then even though the ages are inflated, they should yield relative ages in the correct order. Why? Well, a rock that was a lava that was erupted in the first month of the flood, during the flood would go through 12 months, a year, of accumulation of daughters at an accelerated rate. Whereas a lava flow that erupted in the last month of the flood would only accumulate 1 month's worth of accelerated daughter products. So when you date these rocks, this rock should give an older age because it's had 12 months worth of rapidly accumulated daughters, and this one should give a younger age because it's only got 1 month worth of rapidly accumulated daughters. And so that tells us how we can use these as a relative age, not absolute, but relative ages. And I've summarised it there in that saying. The deeper a volcanic layer in the geologic record, the more time for accelerated reactive decay, so the more daughter isotopes it will have accumulated during the flood year. Thus, these methods may often, not always, be a guide to relative ages of strata, because earlier and older layers would have experienced more accelerated decay and thus accumulated more daughters, and thus would give you older ages. If the decay acceleration factors for each long-age radioactive parent-daughter isotope system could be determined, then the correct absolute ages might be even calculated using these correction factors. I mean, that's a wild hope, but we can see before that there's also contamination, inheritance, that will affect the resultant age, so we have to be careful of that. The point is, I want to make is we don't have to fear radiometric dating as a foe, but rather treat it as a friend, albeit it's a tool to provide relative, not absolute ages. And we can use it also to provenance, that is, to find out the origin or the geographic origin of a sample by looking at its isotopes. So that's where I finish for this first session. Any questions before we go into the break?